Defrost control boards are a subject that in our industry is complicated. I want to simplify that. Today's video is going to be about the anatomy of a defrost board. Let's go ahead and dive into it. Okay, we are now going to get into defrost boards. We talked about heat strips in several videos that we released. We started talking about cold blow when those heat strips don't come on via the defrost control board, going through its sequence of operation. We're going to go over that sequence of operation a little bit more in depth. I've got a board that I'm putting together here. We're going to go through this diagram, one terminal at a time on what's necessary. There's things that we already pretty much have to know. So you may be a little bit ahead of the game if you're watching this video and you're confused. If not, then this video is for you. This video is really for everybody. It's our job to get something out of this. So if you're watching this video and it's a little ahead of your time via experience or other education, go ahead and continue to watch it because you're going to get something out of it. So it's really good. Two terminal blocks that I have up here are the one on the far right hand side of the board, and on the bottom here, these little rectangles that are colored in are going to be input and output terminals as well. We're going to label these together based on what is necessary for the system to run via contactor pulling in, low pressures, switches, high pressure switches, reversing valve coils, outdoor fan motors. We're going to go over the time defrost and the force defrost and cover what should happen there, what voltage we should be reading on these terminals down here and over to the far right hand side. So a couple things to consider is there's high voltage present on this board and there's low voltage present on this board. The majority of all these terminals on the right hand side and on the bottom are all going to be 24 volts. If you have a relay on the board and you have it says fan or ODF or it says OF. There's several different names for it. I can hold up a board here, see what it has. DF, okay, so they're going DF1 and DF2. So there's many names for these terminals, but what it's relating to is the outdoor fan motor. The outdoor fan motor needs to continuously run for the entire duration of a heating cycle or cooling cycle, but during a defrost, this fan motor has to turn off. The reason why it has to turn off is we need to shift our reversing valve over into cool mode, and that's going to allow hot gas to go through the discharge and through the condenser coil, and with that fan motor off, that hot gas will circulate through that condenser coil, allowing the head pressure to rise, leaving the condenser coil warmer and warmer and warmer. Meanwhile, the frost that's built up, that frost will melt off, and then once that cycle is complete, whether it's via timed or the defrost sensor opens, the system goes back into a cool mode. One of the things that I talk about on a video called Cold Blow is these heat strips. They've got to be running during that time because the outdoor unit will essentially be the condenser, and the evaporator will be the evaporator for cool mode. The only thing to cancel out that cold air is going to be some heat strips up in the top section of your air handler running. Now, if those heat strips aren't running, we're going to obviously get cold air dispersed throughout the duct system and into the home. It's not going to be comfortable, and we'll lose efficiency. And so all this is going to be on the diagram, and we're going to go over it little by little. The first thing we need to cover is the 24 volts coming in. So we're going to say first input. I'm going to use an arrow for input. Let me go ahead and get that marked down just a little bit. It's a little bit too big. We'll do that again. The first input on my terminal block is going to be red, which is 24 volts alternating current. And then once we have red there, we have red here. So we're going to say this far left terminal is red. Now it doesn't matter which order I put it in. This is our board. We're building this board together. So I'm just going to go step by step. If I have a red input, I also have to have red for an output also. And we'll cover that in just a second. Now if I have red output, typically the terminal that's right next to that is going to be the DFT terminal. So I'm going to go ahead and put DFT, okay? Let's go ahead and make that a little bit more to the left. So we'll say DFT, there we go. And now what we're going to do is, if we had a sensor over here, which is normally open, okay, and I ran red, okay, 24 volts, over to that open sensor, on the other side of that sensor, it's going to go to DFT. So we're going to go ahead and put an arrow here, and we're going to go ahead and put an arrow here as well. So we know this is a output, and this would be a input. Okay, so the 24 volts that's coming into my board is also the same 24 volts that's always here on the R. And when you see R and DFT, know that the R down here is a output, and the DFT right next to it is the input coming back from the defrost sensor. Okay. Draw a little symbol there for temperature control. All right, so we have R, we have DFT. We're going to go ahead and put a comment on the board. We're going to say this next terminal is a output, and that's C for common. That's their path back to the transformer. And I'm going to say that this next terminal here is common, and so the common here is the path back. So if I said path back, we're saying from any type of coil, whether it's the reversing valve coil or the contactor coil, it needs 24 volts. So I have to have a path back to common. This is my path back, so this would be a input. So input means common, back to the board, through the board, out of the board, back to the transformer. So should be able to leave that there, but I'm going to go ahead and take that out just so we can put it back later on. Okay. Let's look at another terminal. So far, you see, all I've done is I've mirrored my far right side of the board with my bottom left. I'm trying to keep it clean and work on one end to the other, step by step, so we can understand that anatomy. Let's go ahead and use the W. W here is a W here is a output because the board is sending 24 volts to control those heaters. Now, yeah, you're taking the W wire and you're connecting it to a plug, or you're wiring it to your terminal, whatever. But just so you know, this board is sending 24 volts out. So what's happening is during defrost, the 24 volts that is on the board, it's relaying that back to the W terminal, and it's sending 24 volts back out. So these heat strips, can come on. That's what we're trying to do. We're trying to get these heat strips to come on. And the only way these heat strips are going to come on during defrost is if that outdoor defrost control board sends out 24 volts on the W wire. All right, we'll go ahead and put that back. All right. I'm going to undo this last command. So our board's clean again. We could put it back, all these paths back on there later on. We have 2 terminals left. As you can guess, we've got to control the contactor and we got to control the reversing valve. I'm going to go ahead and do the reversing valve first. I'm going to say this is a O type. And as you can see, this is a input. So we have red as an input, common as an output, W2 is an output, and O or B, in this case O, is a input. Down here, the board has got to control the reversing valve. So we'll come over here, put a reversing valve in mind. And a couple things that valve is going to need. One is going to need common. So hence why we have common here. That common is going to go over to the board from the reversing valve and from the contactor. So putting O here, we're going to say we need to make that an output. So this O down here would be an output. Okay, so if we want to connect this, this comes over to the reversing valve coil. Common comes over to the reversing valve coil. And now if I do not have 24 volts on O, then what happens is through the board, because I have 24 volts on the defrost board, I can take that 24 volts and the board can toggle O on and off during a defrost cycle. So that's why that is an output. So even if I were to lose 24 volts here, because we're in heat mode, we still have 24 volts always present on the board to toggle the reversing valve. Very important to make sure all these wires are hooked up. So let's go ahead and take some of this stuff off, clean it up a little bit. Move our reversing valve out of the way. Put it back up here. We're going to go ahead and take our contactor and we'll start talking about the contactor a little bit. We'll make that contactor a little bit bigger so we can see it okay. All right. So we need to take yellow, and yellow might be hard to see. So use this next color over here and see if that makes it a little bit better. Yeah, I think that's a better yellow. It's kind of like an orangish yellow. But this is a input, of course. The thermostat inside tells the contactor to pull in. It has to come into the reversing valve. This is extremely important because this tells the board if it's in heat mode or if it's in cool mode. Now, if you look here, we have a lot of terminals left, and I reserved all these for that last one. So we obviously know that there's high pressure switches and low pressure switches, and if you don't know, they're in series with each other, but they could also be tied directly to the board. Maybe the board needs to have the ability to recognize, so if there's a high pressure event, the board doesn't allow the unit to come on, just in case there's an event like a short cycle going on where the high pressure switch is opening and closing several times within a minute. That's not going to allow the compressor to stay off long enough for pressures to equalize before it comes back on, and that amp draw is going to be very high, and we're going to put damage on that start winding, and that's unnecessary wear and tear. So a lot of the times when you see the high pressure switch and the low pressure switch on the board, you'll see like a diagnostic light or something like that where it tells you, hey, this is what happened, this is why nothing's coming on. And we're going to cover that a little bit in this video. But I like that feature. Anything that's an added safety measure is really good in my book. And if you know me or you know my style of teaching, I like to integrate many layers into the learning. If I give you something that you haven't seen, then chances are you're going to see it eventually. You'll be happy that you got to watch the video. If we look at high pressure and low pressure, I'm going to do this in a different color. We're going to say that one of these is going to be an output, and then one of these is going to be an input. And so we're going to say this is a high pressure switch, and the high pressure switch is normally closed. It's supposed to be closed. And providing that pressure switch is closed, we're making across the switch, and we're going to have excuse me. We're going to have 24 volts back on that board. Sorry, that was hard to multitask here. So we're going to have 24 volts coming out to the pressure switch. Out of the pressure switch, it's going to come back as an input back to the board. And now that board knows that it put 24 volts out. It received 24 volts back. This is the high pressure switch part of the board. And so therefore, the board is going to recognize that there's no faults, and there won't be any lockouts. We go ahead and clean some of this up, and we're going to say that the next one will be a output, and then that will be back into the board as a input. And we're going to say that is a low pressure switch. Same thing, it is supposed to be closed, and providing it's closed, power will come back to the board for the board to recognize that there are no faults and to continue the operation. And so there's another color I'm going to use here in a minute. I'm going to lay on top of this color just to kind of better explain that all these are Y calls. Let me go ahead and clean that last image up. There we go. So this is Y, okay? This is Y. Guess what? This is also Y, and this is Y. All these are Y. So when we get the call for, use black so it shows up a little better, for 24 volts AC compressor to come on for heating or cooling, it's sending out 24 volts on the high pressure and it's sending out 24 volts on the low pressure switch. And as long as 24 volts comes back on the high pressure and 24 volts comes back on the low pressure, then this board's not going to recognize any faults. All it is a pass-through. And so the input doesn't come back through the board and back over here. The input just comes to the board and it stops and says, hey, as long as everything is okay, then we can go ahead and allow our contactor to pull in. Okay? And so we can take our next wire, which would be Y, okay? We'll go ahead and put that down here. Go ahead and go on top of this with yellow so it shows up a little bit better. And that's obviously going to come up down as an output, and that output is going to go to the contactor. We'll go ahead and go over it with yellow, a way we can keep that color in mind. And so we have high pressure switch, low pressure switch, output, input, output, input. Providing all those are closed, we're going to wind up having no problems with Y output of the board to allow the contactor to pull in. And if anybody is confused on another board having, you know, something a little bit different on that, there's going to be more videos that we're going to put out that are going to be very specific to the boards themselves. Right now we're just trying to better understand the anatomy, and we're going to add as many layers to this as possible, so when we get into other boards that are already manufactured and you're utilizing them in the field, we want to make sure that those boards are well understood. So rewind this video as many times as possible so you can understand this part. Past this, we're done with the low voltage. We have a relay here that's normally closed. Normally closed is always going to send power through there unless we're in a defrost cycle. If we're in a defrost cycle, then that relay will be open for that period of time. And basically, we're going to have power on the high voltage side coming in to one terminal, and so we'll say one of those is an input, and it's going to be one leg of power. So we're just going to say 110 volts. It can be L1, it can be L2, and then coming out of it, providing the relay is closed, you also have 110 volts output. And so it's just a pass through. During defrost cycle, we're going to put 24 volts on O. We're going to put 24 volts out on W2, and we're going to open this normally closed relay, and those are the three things that this board is going to do. And then so if we were to look at the commons, if there's any confusion there, we know we have the reversing valve, we know we have the contactor. This common here, even though there's one port, there's a couple of ways to do this. I'm going to go ahead and move the reversing valve, put it down here, and we'll say, if I were to look at my commons, one common would come into the side of my contactor, the other common would come out of this side of the contactor and run up to a side of the reversing valve. So these commons are in parallel at this point, right? And so as long as everything's hooked up to the terminal on the board, and as long as the common's hooked up here, then both of these are going to stay energized, because we could take that path back to the transformer. And so that's you may not have but one common here. Some boards may have another terminal where they have another common. Some boards I've seen them have 3 or 4 commons. The board that I'm holding up here actually has 2 commons on it. So they made it a little bit easier for you. But I mean, if you look at your contactors, there's a couple of spots there, and that's what I chose to do in this video, is just to use those 2 spots and only put one on the board. All right, we need to go over the defrost timer and what the speed up terminal is going to be for. Let me clean some of this up a little bit. We'll go ahead and move some of these images back that we don't need. Put a reversing valve back up here. We'll go ahead and take our contactor, make it smaller, and we'll move it back. Okay. The defrost timer has 3 selectors. If you can look, you can see 30, 60, and 90. What that's for basically is to, if I wanted to set this up for, say, 60 minutes, I can take this pin and this pin and I can jump these 2 together, and that would indicate a 60-minute timer. And what that means is, as long as I'm getting 24 volts here on input for Y and no 24 volts on input for O, okay, the board knows it's in a defrost, right? And so it's going to start calculating, 60 minutes of how long Y was energized. So if you look at that, that contactor can be pulled in for, a 5-minute cycle, right? 15 times, actually we'll say 10 times, and that would put us at 50 minutes, and it may take 3 hours for that unit to come on and cycle 5 minutes 10 times. And in that 3-hour period, we still haven't achieved 60 minutes for this timer to initiate a defrost. Now, you give it another 30 minutes and you may hit 5 minutes again and another 5 minutes again within that 30-minute time. And then at that point, while that system is running, the moment we hit 60 minutes of runtime, that defrost timer is going to initiate a timed defrost. It could take 3 hours for that to happen. Or if the system is running for a very long time for reasons that are mechanical related, or because it's low in charge or something of that nature, or maybe the house just doesn't hold heat very well, or it could be that, it's just really cold at night and the heat pump's just having a hard time keeping up. Whatever's going to initiate a 60-minute run cycle faster, whether it's a 4-hour evening that allows it to go through a timed defrost, or it's an hour over an hour and a half, whichever, it's going to happen. And that's there to maintain efficiency. If the system needs to go into a defrost sooner, we have a defrost sensor over here that can close the moment temperature falls below that 30-degree mark on temperature fall. So the moment that happens, we're going to receive 24 volts back to the DFT terminal, which will initiate a defrost in between the defrost timer's initiation. And then again, same thing's going to happen. We're going to open on our 110 volt output here on the relay of the board. It's going to stop sending 110 volts through that normally closed terminal. The fan motor is going to turn off. It's going to send 24 volts out on W2 for the heat strips to run. It's going to send 24 volts out on the O terminal, shifting the valve over so hot gas can start running through the condenser coil. And that's pretty much it. If you're out here and you're trying to test for defrost on the board that we built here on this diagram, then we're pretty much going to come over here to the speed up, and we're going to jump out these test pins together. There may be a jumper there that you can just push over it where it allows the two to make a good contact. I've used flathead screwdrivers that aren't magnetic. You take a set of keys, put a key in there. Anything metallic would pretty much be useful. Anything to bridge the connection between these two pins. So when that happens, there is a process called speed up. So if we need to initiate a time defrost, we can do it much quicker. There's just a rule of thumb. I'll write it down. For 30 minutes, there's 7 seconds. For 60 minutes, there is 14 seconds. And for 90 minutes, there's 21 seconds. So basically it's for each setting, there's 30-minute intervals between each one. Between each setting, you just add 7 seconds to it. So for 60 minutes, if I don't want to move my timer, I just leave my pins here on that timer. I'm gonna make sure that these two on the speed up are jumped out for a 14-second count, and then I'm gonna release the tool that I'm using to jump that out, and I'm going to let this thing run its course. And while I'm doing that, I'm going to take my meter and I'm going to measure a couple of things. I should hear my reversing valve switch over. I'm going to witness my fan turning off. So within that length of time, the main thing I'm concerned about is measuring voltage between common and W2 to make sure this board's putting 24 volts out at that point in time. If it's not, then I'm going to have cold blow. If I'm getting 24 volts there, and I should not have cold blow. If I do, at least I know it's not from the defrost control board. That's just pretty much it. Past building these boards like we did here, I am going to release one video where we're just using a bunch of relays. These relays that I have over here, contactors, 9340s, thermal disk time delay relays, 9380s. I can do everything that we've got going on here. The time defrost, force defrost, energized reversing valves, toggle condenser fan motors on and off, energized heat strips. I can do that with just a bunch of relays here. I don't need this board. So if you can see how easily we were able to take a defrost board, just draw it in a diagram, look at what's input, what's output, so we know our path of voltage or path of electricity. As long as you know that, as long as you know where voltage is supposed to be, when it's not supposed to be during the sequence of operation, then we can take the manufacturer's intent, whether we build our own board or use a control board that's for one manufacturer and put it on a different unit for another manufacturer. The boards don't know, they don't communicate to the equipment, they don't know what they're working on. All they know is they're designed to receive a voltage and delay or increase and speed up or slow down and put voltage back out based on input and output. And so very similar to relays, it's just a lot more affordable to do it with a board. So boards are printed today, but I think in our industry we lose the ability to understand, if I'm working on one manufacturer like Goodman, I have to use Goodman's latest defrost control board. I can't use anything else. But you'll realize as I release many videos that the pattern that we have here on this anatomy, it's the same. It does not matter, it doesn't change. So I'm not saying that we should put a Goodman defrost board on a Lennox or vice versa, a Train defrost board on a Carrier. What I'm trying to tell you is the train and carrier, they don't know. It doesn't know what it's doing. It doesn't talk. It's just voltage is all it is. So these things are proprietary. They're meant to be installed for the unit that they're working on. Holes wind up lining up, plugs wind up lining up. We're dealing with warranty. We're dealing with people's well-being. So I'm not suggesting that you should go out and be a hero and take a Linux defrost control board and put it on the Amana. I'm not saying that. However, what I am saying is that if you did, it wouldn't know any different and it would work the same. That's what I am saying. Because as long as we're following the sequence of operation and what the manufacturer's intentions were, then it's going to work properly. There's a thing called quiet shift. I'll most likely talk about that a little bit more on another video, providing I can find a board that has quiet shift on it. If I wanted to put quiet shift on this, all I would have to do is, if you think about it, quiet shift. Well, what shifts? O. Well, how do I make O energize my reversing valve? And when this coil gets 24 volts on it and this valve shifts over, how do I make that quiet? Well, one way to do it, if you think about it, is we drop out the output on Y. So if we knock off our contactor, then what happens is we start to equalize the pressure across the valve. Each side of the compressor starts to equalize, and the faster this thing can equalize and then shift over within that length of time that it's equalizing with the compressor not running, then this shift has been done at a lower sound decimal. And then when the unit comes back on, the outdoor fan motor doesn't have to switch. It can just come back on with the normally closed, now open, okay, W2 energize, allowing the heat strips to come on. And you didn't have to hear all that noise, that ruckus that makes people make phone calls because they think their unit's broken, because it's a very violent thing. It also takes off a lot of wear and tear and allows the system to, I believe, run a little bit more reliable. So that's all quiet shift is. And quiet shift is just going to be a time feature that when it goes through a defrost, it's going to allow the W2 to energize, the fan motor to relay to open up, but it's not going to run the contactor in conjunction with energizing the reversing valve. It's just going to allow there to be an additional sequence of time between the contactor being energized and the reversing valve being energized at the same time. If you don't have quiet shift, then everything's just going to happen all at once. W2 energized, reversing valve is going to be energized, and the fan motor is going to shut off, and then everything in reverse order the moment that defrost cycle, whether it be defrost timed or forced, is over. One of the nice features that I like about the input and output on the high pressure, low pressure is if there is a issue with high pressure event or a low pressure event, then it's not going to calculate that as time because the board knows that it may be getting 24 volts over here on the Y terminal, but it knows because it's not receiving 24 volts on high pressure or 24 volts on the low pressure switch, it's not going to calculate any runtime here. So if you could have a defrost board that has something like this to where, it just doesn't go through a defrost, and it doesn't go through a defrost not because it's bad, but because there's a high pressure or a low pressure event that's causing the board to delay that calculated runtime. So your air handler runs pretty much longer than the condenser runs, which could be bad because if your heat strips aren't calling, right, because you're maintaining and your board's not going through a defrost cycle, then what happens is you could be slipping away from the room temperature and the set point, you could be dropping more than 2 degrees, and then of course your heat strip should come on at that point in time, because there is now a 2 degree or more demand for that heat call. And so there could be problems there, and this would be one of those scenarios that somebody would have to put their gauges on a unit to diagnose it properly, and they would realize, hey, there's a high pressure event or a low pressure event, and the board's just doing its job. So, like I said in the beginning of the video, you want to make sure that you're at the right experience level when you're starting to break this down. But if you're not there yet, these are really good videos, because you're going to take something out of this video. If you don't fully understand it, you'll take something away from it that is good. Maybe it's a sequence of operation, that we've covered probably 10 times now within this video. Reversing valve switches over. Heat strips are energized via the W2. Outdoor fan motor shuts off because the normally closed relay now opens during that defrost time. So hopefully this video helps you out. We're going to go over defrost boards with a picture up here on the next videos, and we'll break them down, their inputs and outputs. Thank you for watching this channel. We appreciate it. Please subscribe if you haven't already for more videos to come. Thank you.